This lesson is on empirical and molecular formulas. So recall, when writing a formula for ionic compounds, you need to reduce the subscripts of the ions down to the simplest whole number ratio, because it is just a ratio of the cation to the anion. So for example, what is the formula of magnesium carbide? You say, all right, well, magnesium is in group 2, so it has a +2 oxidation number. Carbide means it's carbon with the -4, so you can do your crisscross and then simplify, and you end up with magnesium 2C for the formula. If you're talking about covalently bonded compounds, molecular compounds, however, you don't simplify them because they consist of discrete particles, so not just a ratio in a big crystal. So what would be the formula for the molecular structure for this compound? What you would do is you would just count up the number of carbon atoms. So we have 1, 2, 3, 4 carbon atoms, and then we have 4, 8, plus 2 more hydrogen atoms, so that would be C4H8, or C4H10. You would not simplify this down to C2H5 because that's not how many carbons and hydrogens it has in it. So looking at some more examples, what are the molecular formulas for these 3 molecules? So we go through and just count up the carbons and the hydrogens. So the first one would be C2H4, next one would be C3H6, and then the last one would be C4H8. Now you can't just look at a compound and say, oh, this has got 4 carbon atoms and 8 hydrogen atoms for each molecule. You have to actually put it into an elemental analyzer. And the way these things work is they will determine what the mass percent is for each element that is in that compound. So just a reminder, we've looked at this before. The way you can find the percent mass is you take the mass of the carbon that's present in the compound divided by the mass of the whole compound times 100. And then you do the same thing for the percent hydrogen. So in the first one, we have 2 carbons. So we're going to go 2 times the molar mass of carbon times 100 divided by the molar mass of the entire compound, which is shown here in the denominator. And you get that it is 85.62%. Do the math for the percent hydrogen, or you could just subtract from 100 since there's only 2 elements, and you get that there's 14.37%. They don't add up to 100 because of a rounding error. So now we go on to looking at the other compounds. Just going to duplicate the equations and the results for the first compound. Go through the math, and you get that the percentages are the same for the other 2 compounds as well. This is because when you're determining the percent mass, you're finding the ratio. So when you are trying to find the formula using these elemental analyzers, you're always going to end up with a simplified version of the molecular formula. This simplified version is called the empirical formula for the compound, because you can find it empirically. So we kind of go on, we say, all right, what is the empirical formula for each of the following? I have a hint at the bottom. It says divide the subscripts by a simplification factor, which is like the lowest common multiple factor. I don't know what the math word would be. So for the first one, P4O6, the factor you can divide out is 2. So you get P2O3. And then C6H9, say, all right, well, 3 is going to be the common factor there. Get C2H3, and then you continue on. For the next one, you would have to add up how many carbons you have. So it's C2, my laser pointer, C2H6O2. And so we have a common factor of 2. So we get that. And then I will let you go on and finish the rest of them. Kind of hit pause, and we'll see if you got the rest of the answers. And So you can see that there are some cases where you can't simplify it any farther, like the bromine dichloride. Its empirical formula is the same thing as the molecular formula. So the way you would find the empirical formula from percent composition, there's a number of steps. First thing you would do is we're going to pretend that we have 100 grams, which allows us to get rid of that percent and just change it to grams. So instead of 5.9% hydrogen, we have 5.9 grams of hydrogen. Can't do anything directly with grams when we start talking about at this level of chemistry, so we're going to convert to moles by dividing the grams of hydrogen by the molar mass, or the GFM of hydrogen. And that gives us how many moles of hydrogen we have. Do the same thing for the other elements. So we take our grams of oxygen, divide by its GFM, gives us moles of oxygen. Now here you can see it's a 1-to-1 relationship. Sometimes the numbers don't work out quite so nicely, so what you can do is you would divide through all of your moles by the smallest number of moles, and that'll give you the subscripts for the empirical formula. So in this case, you end up with an empirical formula of HO. So let's look at another example. So again, first step we're going to do is we're going to pretend we have 100 grams. So we get rid of those percentages. And now we have 47 grams of potassium, 14.5 grams of carbon, 38.5 grams of oxygen. Divide each element by its molar mass. And to get the moles of each element, now we're going to divide through by the smallest number of moles, which is 1.2 moles. And we have 1 potassium, 1 carbon, and 2 oxygens. So therefore, the empirical formula would be KCO2. We have some more examples. So I'm just going to give you the molar amounts. So you end up with half a mole of palladium, 1 mole of chlorine, 1 mole of carbon, 2 moles of hydrogen. Divide by the smallest number of moles, and you would get this ratio. So the empirical formula would be PdCl2C2H4. Do the same thing for the fourth example. When we get these, we're going to divide by our smallest number of moles, which is the 0.86. We get 2 nitrogen, 8 hydrogen, 1 sulfur, and 3 oxygens, which gives us empirical formula, which works out to be the same thing as the formula for ammonium sulfite. All right, so now if you want to go from the empirical formula to the molecular formula, back to the unsimplified version, you got to figure out what that simplification factor was. So here we have benzene, and the molecular formula is C6H6. The empirical formula, common factor, is 6, so just be CH. So the simplification factor in this case was 6. When I'm telling people how to find these simplification factor, I talk about a big GFM and a small GFM. The big GFM is given to you in the problem. You can't figure this out yourself. You have to be given this value. And this is the molar mass for the molecular compound, the unsimplified one. And it's going to be a larger number than the small GFM, which is just the molar mass of just the empirical formula. The way you find the factor is it's going to be the larger number divided by the smaller number. So put those numbers in there, and we get that the simplification factor, which we already knew, is equal to 6. So we go on to the next one. We have an empirical formula. We're just given an empirical formula of CH2O. And you're told that the simplification factor is 4. So we're going to multiply all those subscripts by 4. The molecular formula would be C4H8O4. So this is why finding the simplification factor is important. It allows you to get back to the molecular formula. All right, so back to those examples we were looking at when we were doing the empirical formula. So we had our first example, which had an empirical formula of HO, where the molar mass that we're given, this is the big GFM, the one for the molecular formula. So the empirical formula is HO. We find the small GFM, 17.01. Our factor is going to be 34.02 divided by 17.01, which is 2, which means that the molecular formula is H2O2, or hydrogen peroxide. Do the same thing for the next example. So we divide through by the smallest number of moles. We're given what the molar mass of the molecular compound is. So the empirical formula is KCO2. It has a small GFM of 83.11 grams per mole. So our factor is going to be 166.22 divided by 83.11, gives us a factor of 2. So our molecular formula is K2C2O4. And this is potassium oxalate, and it's related to the compounds that make rhubarb taste as sour as it does. All right, so our last two examples, our empirical formula is PdCl2C2H4. We have to find the small GFM, which is 205.38. So we're going to take our big GFM and divide by the smaller one. We get a factor of 2, which means that the molecular formula is going to be PD2Cl4C4H8. And then we have our ammonium sulfite example. We have the small GFM is 116.07. The molar mass that we were given is the same value, so that tells us that the molecular formula and the empirical formula are the same. And that's pretty much it.